to exercise the review of Laplace transform. So for these questions, basically you're looking for should be something that on the denominator have the second degree. So this could be 1 and this could be 1 here. And so here the first way is you have to try your best to come up with the pattern that's showing up in the tables. Okay. And for me, I can look at in the denominators, I can try to reorganize the terms in the denominator such that that'll be the summation of a square term plus something. And such that I try to fit into either of the two forms. Okay, I will try. So basically here the 4s squared plus 4s plus 20. If you use the first two as the first two terms as a hint, so something s plus something squared will be, once it expanded, that'll be equal to s squared plus 4s. Okay, so in here you can quickly identify that should be 2 here. Okay, so, and then of course here that extended will be 4. So in this way here, give you the hint, you expand it into this form. Okay, and this one expanded equal to this. So to make this one equivalent to this one, so that means you have to plus 16. Okay, because here expanded it has a constant 4. 4 plus 16, that is equal to 20. So here that is a hint, give you the something here. Okay. So we have this one. At least we have the denominator come up with the patterns we need. Okay. And now we look at either we take sine or cosine. Sine is with the numerator that is a constant. Cosine is with the numerator that has s. And for this example, each numerator has the constant. So basically, we're expecting the Laplace transform must be into this pattern here. Okay, so we identify we have to use this one. So let me rewrite the pattern there. So b as minus a squared plus b squared, and this one putting 2 is this. Basically, this one is equivalent to b as squared plus b squared, and we do replacement s replaced by s minus a. Okay. So in this way, we know from the tables here, this pattern is, once we convert it, is equivalent to psi bt. Okay, if we only look at this pattern here, and that transform, inverse Laplace transform equal to sine. Okay, and here we have a replacement. So that means we adopting the right form, that should be this one. So with this replacement here, then we know that we have the 80 multiplied here. So that kind of the sequence applied to here. From here, you rearrange the things. So the first one is you identify this one will be equivalent to. Let us do the replacement first. So here, replace s by s plus 2. So this is the patterns like this. Okay, so now you come to the generic patterns. Then you try to work on to fit into the right format. So here give a hint, s squared plus b squared, s squared plus b squared, and b is 4. Exactly here is number 4, so you don't have to do anything. So from here, it converts into sine bt, b is equal to 4. And here we have a replacement here, so that means in the Laplace inverse, and that is minus 2t. Good? Okay. try other example here. You good? Okay, the second example I want to try is this one. And you keep writing, then I occupy this space later on in the increase this one here. So we're going to calculate the Laplace inverse of this function is here, and this is 1, s plus 1 cube, and s minus plus 2. Okay, so right now for the second one, we on this example here. This one again, you can see we can factorize into a few terms, and for this example, a little bit different from the previous one is here. For s plus 1, it has to the power 3. Okay, so this is a little bit different from what we have done before. So for this s plus 1 to the power 3 and s plus 2. So here I'm going to show you the how we did it for this one for factorizations. So again, once we want to factorize in a complete form. And to a complete form is in such that here s only have to the first power, so we have this form here and multiply with a. And for s plus 2, and it's in a similar way, and we factorize s plus 2. And for this one, let me say the coefficient using c, okay? And now for s plus 1, it has to the power 3. When we factorize, it could have the right form, including s plus 1, and also have a possibility s plus 2 appeared, and also have a possibility appear with this form here. So I think when you do the factorizations, to make the factors terms complete, and that means you have to include all the possibilities. Although here showing up is only to the third power, but when you factorize, you have to make the complete combinations. Be good? So here the coefficient, let me call this a B1, is a B2, is a B3. Okay, so for this one, and this factors term will be complete. And here we have 5 coefficients to determine. Again, you can recombine the right-hand side and then compare to the coefficients with this one. Okay. Maybe I just maybe I just use the quickest way. Okay, we can do this one. So to determine A, if you want to determine A, then again, your goal is to have the A stand out without anything. So to have the A appear like this one here and compare to the first one, you have to multiply the both sides with S. Okay, so multiply with S and A will stand out, but the remaining terms will be multiplied with S. Okay, so basically let me copy this one here. Okay? So remaining 4 terms will be multiplied with S. And to determine A, then basically is to numerically disappear these remaining terms. To get that done, then simply is this. You set S equal to 0. When you introduce the value of S equal to 0, basically the remaining terms is gone to 0. So which means A equal to this one. You good? Okay. And this is the down we have done last time. Okay, to determine C in a similar way. So if you want to have the C stand out, okay, so then you see that we multiply every single term with S plus 2. Okay, so that means the first 4 terms will be multiplied with S plus 2. Okay, so basically here that is the first 4 terms. inherited from the previous equation here. So again, to determine the value of the C, then you can see by observing the right-hand side, if you introduce the value of S equal to -2, then that will lead in the whole terms will become 0 when S equal to -2, right? So when S equal to -2, the whole term becomes 0, so the right-hand side has C only. So basically C can be determined by this. Okay, so the value of this one will give to C. So here, from here, then A equal to 1/2, and then A equal to 1/2. So here the C equal to 1/2. Okay. Good. So that is the same thing we did last time. So now, yes.
Minus 1/2. So we have -1 cubed.
Yes. So -2 here.
Oh, never mind.
No.
I think it's fine.
No, half. Okay.
It's possible.
Okay. So any questions? So that is the same as we did last time. And to save space, I want to erase this one. And right now, I want to demonstrate how to determine B1, B2, and B3. Okay. Determine B1, B2, B3, we have a sequence. And the sequence is to determine B3 first, then B2, then B1. And the sequence is like this one. In a similar fashions, and let us multiply the both side with the s plus 3 to the s plus 1 to the third power. So this okay. So here let me write everything out. So here I multiply the both sides with the highest order terms, and that appear here. Okay. So from here you observe the right hand side of this equation. You can see right now B3 stand out alone. So we can use the similar concept and try to find a good number. Try to find a good number for S such that the remaining terms on the right-hand side disappear or become to 0. Then the B value, B3 value will be that one, right? So you can see for every other terms on the right-hand side, they contain the term s plus 1 or its power. So that makes the selection very easy. You can see we simply set s equal to -1. This term becomes 0, becomes 0, becomes 0, becomes 0. So B3 stand out. Okay, so in this way, B3 will be equal to simply is this term here. Be okay? When we set up in this equation here, we set s equal to -1, then basically this term becomes 0. This term becomes 0, this term 0, this term 0. So B3 appear. Okay? Let me remove the B3 term here. So this is B3. Let me box it. Okay, and now we want to determine B2. And to determine B2, okay, let me rewrite the things. So to determine B2, let me rewrite everything. You stay with me. So right now our goal is to determine B2. And the same concept, we wish the B2 can stand alone on the right hand side. Everything else will disappear or become to 0. Okay, so to do this way, you can see B2 right now multiply with this term. How to get that term away? Any idea?
Divide it out.
Divide it out, cancel out,
But then we'd end up dividing by 0.
divided by 0. So dividing won't be good. Okay, if we try to dividing out, then leading to the denominator will become singularity. Okay. Another way is we take the derivative, we take the differentiations. We take the differentiation, we derive, how to say, we take the derivative on the opposite side. Sometimes I couldn't pronounce some kind of words. So here, if we take the derivative respect to s on the opposite side, and you can see basically here, this one is ds on the whole terms, okay? And I know that will be complicated. And once we take the derivative, then so let me take this one here. So basically derivative on the both side that become ds, and I simply rewrite everything here. Okay, and then this term derivative ds and as and s plus 1 cube. Okay, you don't need to implement the things at this moment, and just be with me. And this is s plus 1 times 2. Okay, then this one will become B2, and this one becomes 0 because that's a constant. And this one dds, and c s plus 2 and s plus 1. Okay, something like this one. So once you do the derivative on the both side, then you have this one. So once you have this one, you can see the B2 appear alone. So remaining is to disappear the remaining terms. So from here you can see, for this term, if we taking the same concept, say pick the s value equal to -1, then this term becomes 0. How about for this term? You see, although this term appears a little bit complicated, but without calculation, you should be able to see the results should be containing the term like multiply with s plus 1 squared, something like that one. So basically this one, once you introduce an s equal to 1, this one will be go to 0. Okay, if you want to be more cautious, you can do it. You can implement do the partial derivative, and then you can check. Okay. In a similar way, this one, after the first order of the derivative, then again, this will be expanding in terms of a combination containing the s plus 1 term. So when s equal to -1, this term becomes to 0. Okay? So in this way, this one will leading us to B2. So basically, B2 is equal to this. Okay, and how to determine this one? I think this should be straightforward. To calculate this one, b ds, and you can pre-multiply this one, become s and s plus 2, and s equal to -1. Because here you can see the two terms cancel out, so that can lead into a little bit easier form to start with. Okay, so here if you calculate B2 carefully, and B2 should be equal to 0, and that is a calculation result after implementing this one here. Okay, so this one equal to 0. Be good? Okay, now we continue to on the B1. B1 again, B1 is a coefficient of s plus 1 squared. So this one again, we want to have a V1 standout. Similar concept. We simply take the double derivative with respect to s on the opposite side. Okay. So that means here, let me write down this one quickly. V1 will be equal to d squared ds squared s plus 1 q s plus 2 and s plus 1 s equal to minus 1. Okay, so this one the same concept like we did here, so we don't need to write out everything. So simply we take that concept and then that will be the number here. So after this calculations and B1, B3, let me double check with my, so B3 equal to minus 1 and B2 equal to 0 and B1 equal to minus 1. Okay, good. So we can have everything replaced here. So that will be 0.5 and this is 0.5 and this is oops, 0.5 and minus 1, 0 and minus 1. Okay. So now we have the things here then. Basically, we try to map the things and the terms one by one. So the Laplace inverse of the whole thing is, the first one is constant divided by s. So we look for this term here. So 1 over s is inverse is constant. So basically this term is 0.5. 0.5 is a coefficient and multiply with this one here equal to 0.5. Okay. For this one, so that's 1 equal to minus 1 times Laplace inverse of 1 plus 1 over s plus 1. So that term correspondingly is this one. So you introduce a equal to minus 1 here. So basically this one equal to 0.5 minus e minus t. Okay, and then this term equal to 0, and this term is minus 1 Laplace inverse of s plus 1 cube. Okay, so they should be equal to minus something. So right now we handle this one here. And how to do this? Push patterns. Now your turn.
Bottom left.
You instruct my finger.
Bottom left.
This one?
Down.
Okay, down.
Down.
Down. This one? Good. Okay, we pick this one. Actually, this one you can visualize. This one as the in a similar way. This is the similar pattern like this. And no, let me start over. This is a similar pattern with this one, and the two are similar, and we simply do the shifting. So let me explain this one here. This is ft, and we have a t to the nth power. And this is the plus transform, and that one equal to n factorial and s n plus 1. Okay. When we have the replacement in S, so which means if we have the same patterns, okay, and right now in this pattern, we have a replacement in S. For example, S replaced by S minus A. So once we have the replacement, basically this term simply is equal to n tilde S minus A n plus 1. Okay, so that is an equivalent description like this one. So basically that is the same is this form here. So once we have a such replacement, and just like we have done in sine and cosine, basically in the corresponding inverse in time domain, that is corresponding is this. You take the same patterns as the generic one. And here, because we have a replacement in the S domain, we put a shifting in the S domain. Corresponding in the time domain, we multiply with E, A, T. And this one, I say this is called the, okay, in my words, I call this called the replacement of S by S minus A, and that's my words, but in terminology, they call the shifting in S domain. Okay, and that is corresponding to the shifting theory. And that one is here. Okay, this one. When we have a shifting of the value as in the S domain, that corresponding is to multiply exponent in the time domain. So basically in generic, I simply refer is this form here. Okay, so in the same, previously, we applied that shifting theory to sine and cosine. And also we can apply to the exponent function of t. Okay, so for this one, we apply the shifting theory, and either you can adopt either one. So here that should be equal to E, and right now for this shifting, so that corresponding A equal to minus 1, so E minus AT. And this term basically becomes is 1 as generic form is this one. Okay, that is generic pattern. And to fit into this one, that should be equal to S3 and 2 to the power, and then to make that equivalent, we multiply with 1/2. So this one gives us is t to the square. So multiply with the scaling factors, so that is 1/2 times t squared for this. Okay, good? Okay. Then the final term should be very straightforward. The final term is a plus inverse of this one. The coefficient is 0.5. And the plus inverse of S plus 2, that corresponding is E minus 2t. And then again, we take this one here. Okay? Thank you. No.